Right, so for these we're going to do some examples of applications of exponential functions. These are the most common examples that you're going to see in an exam situation, and the examples I'm actually going to do here are from past papers. Okay, so the first place to start, we've got question 9. I've copied and pasted these in, so I'm not sat writing them out. The value V in pounds, like in million pounds, of a cruise ship T years after launch is given by the formula V equals 252 e to the power of negative 0.06335 t. Okay, so for part A, we've been asked to find its value when it launched. So at launch, t would be 0 because it's not. In the question it says years after launch, so at launch the t is 0. So for part A, we can just substitute that in. So we get 252 e to the negative 0.06335 times 0. So that's just 252 e to 0. And we know that e to 0 is just 1. So we get that it would be 252 million. And that's our first question. So that's its initial value at launch. So for part B, we've been told that the owners will decide to sell the ship once it falls below 20 million. After how many years will it be sold? Okay, so we know that we want the value to be less than 20 million, so we can put it at 20 million, and that'll give us when it reaches 20, and then just any time after that it'll be below that, so that'll work, and that'll give us our answer. So any time more than what we get, so any value greater than the answer we get for t when we solve for 20, that'll tell us when it'll fall below. Okay, so we can kind of substitute this in. So we have V equals 252 e to the negative 0.06335 t. Okay, and then we substitute in, so we're going to get 20 is equal to 252 e to the negative 0.06335 t. Okay, so before we can do anything that's actually going to help us out, we need to get the e on its own on that side of the equation. So we're going to have to divide both sides by 252. So we get 20 divided by 252 is equal to e to the power of negative 0.06335 t. Okay, so the t that is what we're kind of aiming for is kind of all bundled into that e. So we can rearrange, because we know that any exponential we can rearrange into being a logarithm, and that kind of frees up whatever is the power. So the e, we know that that is the base of our exponent, and so it becomes the base of our logarithm. So that means we're going to have a natural log, because log to the base e is just the natural log, and our 20 divided by 252 goes in there. There's no point changing that into decimals or anything. We could simplify it, but we're going to try and find just a value which we're going to have to plug into a calculator anyway, so we might as well just leave it as it is for now. So we get negative 0.06335 t is equal to the log of 20 over 252. So then just to get t on its own, we can divide that log of 20 over 252 by that negative, divide it by the negative 0.06335. We put that into our calculators and we get 39.995, and then it just keeps going. Okay, so because it's asked us after how many years it'll be sold, it's quite nice to put like a little sentence at the bottom. Okay, so this means that, so we could write the boat will reach a value of 20 million. Okay, after approximately 20 years. Not 20 years, 40 years. halving its value, so 40 years, after which it will be sold. Okay, so that's an example of that, and we'll have one more example just in a second. Right, so question 2. This is quite a good real world application of exponentials and kind of where they're used in real life. So we've got, it's claimed that a wheel is made from wood which is over 1,000 years old. To test this claim, carbon dating is used. The formula a to the t equals a naught e to the power of negative 0.000124t. And this formula is used to determine the age of the wood, where a naught is the amount of carbon in any living tree, at is the amount of carbon in the wood being dated, and t is the age of the wood in years. For the wheel, it was found that at was 88% of the amount of carbon in a living tree. Is this claim true? So it's asking, is this wheel over 1,000 years old? And we've got to use this equation to figure it out. Okay, so the equation we get, we've got at is equal to a naught e to the negative 0.000124t. Okay, so from the equation, or not the equation, from the question, we've been told, well, we know at is what it is now, a naught is what it was to start with, and we've got to kind of find, and t is what we've got. Those are our three variables in this equation, the three things we don't know. And the thing that's going to help us is this. So at was 88% of the amount of carbon in a living tree. So a naught is the kind of standard on a normal tree. And we know that at is 88% of that initial a naught. And we can rewrite that as a decimal as 0.88 A0. So now we've got two things that we can kind of substitute in, or one thing we can substitute and then see where that leads us. So we get 0.88 A naught is equal to A naught e to the power of negative 0.000124t. Okay, so when we've got something on both sides of our equation, and they're both multiplying because it's 0.88 times that and A naught times those, we can kind of cancel those out. So we get 0.88 is equal to e to the negative 0.000124t. Okay, so same as the first question, from here we can do natural logs. E is the base of our exponent, so it's going to become the base of our logarithm, so we have the natural log there. We're going to have that 0.88 in here, and that's going to be equal to negative 0.000124t. Okay, so now we can divide through by that negative, so we have the natural log of 0.88 divided by negative 0.000124. Again, it's just a case of plugging it into our calculators, and when we do that, we get 1030.914. And if we round that, we're going to get just 1030.91. And that is in years. Okay, so again, we need a kind of sentence. So therefore, the claim is true as the tree is 1030 years old. Right, okay, so that's some of the applications of exponential functions, and we'll go on and we're going to do an application of logarithmic functions.